Hi, let's look at some examples of categories. So the first one I want to show you is this one, the category of monoids and monoid morphisms. So here the objects are monoids. Remember, these are sets with a binary operation and a unit, and the morphisms are structure preserving maps between these things. So we have our category here, and then each object is a little monoid. So this could be the natural numbers with plus and 0, and this could be the integers with times and 1, for example, and there's many other monoids, of course. And then the arrows between these things are functions between the underlying sets that preserve this structure in an appropriate sense. Right. Okay, and then we can make the identity to be the underlying identity function plus a proof that is structure preserving, and we can make a composition the underlying composition with a proof that is structure preserving. And the fact that this is associative and the identity really is an identity follows by associativity and identities for the underlying functions plus uniqueness of identity proofs for this proof part here. Right, so let's see if we can do this. So here I defined what it means to be a monoid in Agda. So I said that to be a monoid is to have a carrier set and a binary operation and a unit, and then proofs of associativity, identity, and identities for this operation. And here I said what it means to be a monoid morphism between A and B. So first I'm just giving myself some shorthands for A and B, so that I can say that first of all there needs to be a function from the carrier of A to the carrier of B. So that would be from the natural numbers to the integers, for example. And then I need two proofs. The first one is that I preserve the unit. So if I apply the function to the unit of A, then I get the unit of B. And secondly, that I preserve the multiplication. So if I apply the function to a multiplication, then I get a multiplication again of the corresponding things. And then here's the technical thing, where to show that two monoid morphisms are equal, I'm saying that it's enough that the underlying functions are equal. And see that this is implemented using uniqueness of identity proofs. But let's not worry about that. Instead, let's see if we can define this category. So I want to define a category, which means that I have to fill in these fields of the category. So I can do that by pattern matching and then splitting on the result. I just press enter immediately, and then I get the fields I have to fill in. Okay, so I want my objects to be all monoids, and I want my homomorphisms to be all monoid morphisms, right? Because these are the structure preserving ones. And then here I have to give an identity monoid morphism. So if I split on the result again, I see that I have to give an underlying function, and then I have to prove that it preserves the unit and multiplication. Okay, so my underlying function should be a function from the carrier of A to the carrier of A. Well, I'm going to use the identity function for that. And then it's going to be really easy to show that this preserves the structure, because it doesn't do anything to it. Right? So this is true by REFL. And here, if I take an X and a Y, then here it's a little bit hard to read because Agda is not very good at printing parameterized things, but we see that these are in any case the same on both sides. So REFL works again. Right. Okay, for the composition it's the same thing. Okay, we have to compose two functions f and g, and then we have to give the underlying function. So this is going to be the composition in set of the underlying function of f and the underlying function of g. It's just composing the functions, and then I have to prove that it preserves things. So here, let's see. So I know that f preserves this unit. Let's see if I do preserves unit f. Okay, then I can do a conf g of that. I do enough brackets. Okay, that looks like a good start. So if I do that first, and then something else, then I have this step left, but this is just the fact that g preserves the unit. Right. So, okay, so I can do that with a trans or an equational reasoning. And then here, say for every x and y, I have to say this horrible thing. So actually I've prepared a more readable version of this that we can slot in here. There you can see what it says. So I don't have A, B, C in scope. Let's put them in scope. Okay, so this is what we're actually asked to prove, that if we take this composite and apply it to x times y, then we should get the composite applied to x times the composite applied to y. Right. Okay. So let's see if we can do this. Well, we know that f preserves this multiplication, right? So this should be the same thing as f of x times f of y, I hope. Okay, and then here we see this step is that g preserves this multiplication. Right? So this should just be preserves g of something and something, which Agda can infer for us. And this should be con of fun g and the fact that f preserves it for x and y. Okay, so we could do that. So we've given the composite, and then we've shown that it really is a monoid morphism. That's preserved the structure. And then here we have to show that this composition is associative. Right? So this is exactly where we're going to use this little helper function, which tells us how to prove that two monoid morphisms are equal. So we only have to give one more proof, that the underlying functions are equal. But these are functions, so we saw in the previous video that this is actually equal up to reflexivity. So we can just give refl here, and it's going to be the same thing for the identities. So this is quite hard to prove if you don't have this helper function, but once you have it, it's really easy.